So this is an introduction to naming and formula writing of ionic compounds in section 2.8 of your textbook. So when naming or formula writing for ionic compounds, remember that they contain two kinds of ions. The first one is called a cation, and it's the positive ion, and it's always listed first. The formula always has the cation first, or the name always has the cation first. And then in the middle, there's a charge, and the charge is listed as a Roman numeral. Roman numeral 1 meaning a positive 1 charge for the cation. Roman numeral 2 meaning a positive 2 charge for the cation, etc. If you had a Roman numeral 5, it would mean positive 5. 6 would mean positive 6, etc. So knowing your Roman numerals is important because it tells you the charge of the cation. The Roman numerals only occur in the name. When you have the formula identifies the charge by how it connects with the anion, which is the last things listed, or the second thing listed. And the anion always has a suffix IDE, with the IDE suffix connected to it. Here's some examples. Copper 2 chloride. Copper would be the cation, it's listed first. 2 tells you that copper has a charge of positive 2, and chloride tells you that the second element, the anion, is chloride. And the formula would be CuCl2. Why there's a little 2 down here is coming in the future. Here's another example. Iron 3 sulfide. So iron is the cation. It tells you that iron would have a positive 3 charge, and then sulfur would be the cation, and it would end up being Fe2S3. You'll find out why those little numbers are there soon. Here's a third example, cobalt 2 oxide. Cobalt is the cation. It would have a positive 2 charge because there's a Roman numeral 2. And oxide, of course, would be the element oxygen, and it's just COO. Now, if it's a group 1 or group 2 cation, or a few special ones on the periodic table, then they don't need a charge. They don't need a Roman numeral listed with them. For example, potassium iodide. Since potassium is in group 1, and we know that it's always positive 1, you don't have to put the Roman numeral 1 in there, and that would just be Ki. Or strontium phosphide. Since strontium is in group 2, you don't need a Roman numeral 2 with it, and strontium phosphide would end up being Sr3P2. Why the 3 and the 2 are there is coming in the near future. The other special elements that don't need these Roman numerals are listed on this periodic table, and you should list them on your periodic table as well. Silver always has a +1 charge, so you can put a little +1 next to it. Cadmium always is +2, so you can put a little +2 next to it. And its partner zinc that's right up above it is also always +2, so you can put a little +2 right there. And then the element aluminium or aluminum is always +3, and so you can put a little +3 up there. See how they kind of make a little S on the periodic table, meaning special. Those 4 special elements, including these group 1 and group 2s right here, do not need the charge listed in between them. So now that you have a little bit of background about which ones are special and which ones, what the format of a formula and a name looks like, let's look at naming the binary, meaning 2 kinds of elements. The prefix bi means 2, binary. 2 kinds of elements, ionic compounds. Ionic compounds means that there's an anion and a cation. And we'll look at lots of different examples of the names and formulas, and I'll explain to you how each one of them comes about their name or about their formula and vice versa. So first, let's look at some formulas. Let's look at some formulas and some names and look at how you would write the formula. So for example, let's take chromium 3 bromide. Now to write the formula, we would write the symbol for chromium, look it up on the periodic table, and it's Cr. And before you finish writing Cr down, notice that it's a 3 right here, meaning that it's got a positive 3 charge. And when we write cations, we always put the positive 3 in the upper right-hand corner, indicating that it would have a plus 3 charge. And then bromide, we'd write it right after it, and look on the periodic table and find out that its anion charge would be -1 because it's in group 17, and there's a little -1 up above. Now, there are several different ways to attack this, but we know that since this is positive 3 and this is -1, they don't form a neutral compound. Positive 3 plus -1 do not equal 0, and 0 would indicate it's a neutral compound. And so we need to have a certain number of each of these cat and anions to make it so there'll be 0 of them total. As a matter of fact, if I had 3 of these -1 charged bromines, I would now have positive 3 plus -3, and I would be an even number, or I would be zeroed out, or I would have a neutral compound. The way to indicate that there are 3 of these is to write the formula CrBr with a little 3 down below it, indicating that 3 bromides exist. Now you could get the same formula by doing what's called crisscrossing, Cr positive 3 and Br -1, and crisscrossing the -1 and the 3 right here, dropping the charges and swapping the numerical values. And remember, you could write a 1 right here, but it's always assumed that there's a 1, and so you still end up with CrBr3. This works most of the time, and so the crisscross or drop the charge, drop the positive, negative, and swap the charges works okay, but I'll give you a couple examples where maybe it's not the best. You can never go wrong by saying, oh, they've got to add up to equal 0. How many of them do I need to make sure that it adds up that way? Here's a second example. Calcium, phosphide. Now notice I didn't put a little Roman numeral in between because calcium is one of the special elements, and it's over here in the positive 2 group. And so when I write the formula for it, I would write Ca positive 2, and phosphide is in group 15. It has a -3 charge, and so I would write 3 with a little -3 here. And if I follow my idea of this would be positive 2, and this would be -3, I'd see that immediately it doesn't add up to 0, and I would have to have multiple calciums or multiple phosphoruses to make it sum to 0. As a matter of fact, you savvy math people probably notice I need 3 of these, and I need 2 of these to make sure that it adds up to equal 0. This 3 then becomes the subscript for the calcium, and the 2 becomes the subscript for the phosphorus. And there are those of you that are watching and saying, yeah, but I could have just as easily swapped the 2 and the 3 right here and dropped the charges, and I would have had the same thing. And you are correct. It does work just fine that way. Here's one where it doesn't work quite as well. Tin, 4, oxide. So tin is right here, and notice how it can be plus or -4. In this case, they're telling us it's 4 because there's a Roman numeral 4, so we write Sn, positive 4. And then oxygen is in group 16, and it has a -2 charge. Now, if I crisscross these charges, drop and swap the charges, I end up with Sn2O4. But that's not the actual formula of it, because if I do the adding them up, I have positive 4 and -2, and it's got to add up to 0. It tells me I only need 2 of these. Oh yes, and so I really only need a subscript of 2. So SnO2 is what my formula should really be. Some people will say, well, yeah, I could have just reduced this. And yes, you can. You can go ahead and reduce that to a single whole number, but knowing how to do it both ways, I think, is extremely valuable. Let's do one more. Let's try one also with a Roman numeral here. Let's see if you can do vanadium 6 sulfide. Okay, it tells you that the V is positive 6, and the sulfur you have to look up here and here is negative 2. And you can say crisscross them, but remember you're going to end up with not, something you're going to have to reduce. So you could also say positive 6 plus negative 2 equals 0. Oh, I'm going to need 3 of these. And so it ends up being VS3 as your best formula. Let's see if we can do some going the opposite direction. And now we'll go from the formula to the name rather than the name to the formula. So I still will have name over here. Now I'm going to put formula over here. And this time I'm going to give you the formula and we'll see if we can come up with a name. So let's try this one as an easy start. CAS. Okay, remember when you write the names and the formulas, the cation always comes first. And then if you need to put a charge in the middle, you go ahead and do that. Most things have the charges, but remember there's a few specials. And then you name the anion second, and you add the suffix IDE. So this one we'd call calcium. And then we notice that calcium's in this group that's positive 2, so you don't have to worry about putting a number in the middle saying it's charged because it's a special one. And then we'd put sulfide, and so we'd call this calcium sulfide. Let's try a second one. Let's do Fe2O3. Okay, for this one, name the cation iron, Fe, and then name the anion oxide. Leave some space in between because you know that iron is going to need that charge or that Roman numeral that indicates what its charge is, because iron is right here. It's not one of these special guys right here that you wrote on your periodic table. Now, figuring out what that charge is for many people is really tricky, and this comes back to you using your periodic table to figure out what it is. Look at oxygen. Oxygen is -2. There are 3 of them. There are 2 irons in this formula, and iron has some charge. And I know that it is going to be a neutral compound, so it's going to add up to equal 0. And now you can guess and check or do a little bit of algebra, and you'll find out that the charge of iron must be +3, so you need to put a Roman numeral 3 in the middle. Iron 3 oxide. Let's do another example like that, and let's see if you can figure out the charge. And then I'll save a tricky one for last. Let's try Ti, and we'll put Cl2. So look and find Ti on the periodic table and know that's named titanium. And then Cl is over here, and don't forget to put an IDE suffix on it, so call it chloride. Leave some space for that Roman number in the middle because you know that titanium's one that's going to need a Roman number. And you might be able to figure it out right away. Titanium is some charge. Chlorine's a -1 because if I look on the periodic table, it's in group 17. There are 2 of them, and it has to add up to equal 0. So what does titanium's charge have to be? Well, it's got to be Roman numeral 2. Okay, some people probably saw this, that, oh, if I uncrisscross these, 2, oh, that's the Roman numeral. 3, oh, that's the Roman numeral. That works most of the time, but not always. So you have to be kind of careful with this. And here's the last example, well, another example, and it's a tricky one like this. Let's try formula of, let's use zirconium, and we'll make it zirconium with sulfur. All right, let's see if we can name this. Zr, zirconium. And S, remember it's sulfur, so you have to put "ide" at the end, so sulfide. Now if you were following what I did and just uncrisscrossed them and put a 2 there and said, oh, it should be Roman numeral 2, this time you'll be unfortunate and you won't get it correct. And so you need to be able to know that these are going to add up to equal 0, and whatever zirconium's charge is, plus sulfur, which is in the -2 group, times 2 equals 0. And so this would have to be positive 4, and so you'd put a Roman numeral 4. See how it can be kind of tricky? So these are binary ionic compounds. These are binary ones that have 2 kinds of elements. One of them's a metal, one of them's a non-metal. But what happens if there are groups of elements that come together that also have a charge, and therefore you have 3 or more elements in a compound? Well, these are called many atom ion containing compounds. They're still ionic, meaning that they have a positive cation and a negative anion, and that they have to add up to equal 0, the positiveness and the negativeness. But these many atom ion containing compounds now contain special groups of elements that make what are called a poly, meaning many, atomic ion. Now there are many different polyatomic ions that are listed in your textbook and on the back of your periodic table. I'll give you these poly or many atom ion examples. NO3 together is a -1 charge, and it's called nitrate. SO4 -2 is a many atom ion, and it's called sulfate. NO2 -1 is called nitrite. SO3 -2 is a many atom ion called sulfite. And you may have already recognized a pattern that if you have more atoms of oxygen in these, it has the ate ending. If you have less atoms of oxygen, it has the ite ending. Here's a couple more. CO3 -2 is called carbonate. And OH- has a funny name. It's called hydroxide. Notice most polyatomic ions end in ate or ite, but there's a few that end in ide, and there's a huge long list on the back of your periodic table. Well, when you name or formula write many atom ion containing compounds, you do it very similar to what we just talked about with binary, where we have the cation listed first, and then we have the anion listed second. But if the anion, or the cation, if the anion is one of these types of anions right here, then there is no suffix change needed. You still should use the Roman numeral or the charge in the middle if it is a cation that is one of the normal cations, not one of the special ones right here. You should still put that in the middle. And let's do a few examples where we have the name over here on this side, and then we'll have the formula over here on this side. So here's a name. Let's do sodium carbonate. So we find the element sodium on the periodic table, Na. And then we find carbonate on our list of polyatomic ions. And this one is CO3, and notice it has a -2 charge right here. Looking on the periodic table, sodium is in group 1 and would have a +1 charge. And you could crisscross, or drop and swap, drop the charges, swap the numerical values, or you could sum them to 0 to make sure you're doing it correctly. +1 plus -2 is equal to 0. I will need 2 of these sodiums, and so I'll take this little number 2 and put it right here below the Na, and so the correct formula is Na2CO3. Let's do an example that's backwards of that. Let's take this group, Al, and then let's put a 2SO4 3. So looking at this one, name the first element. Al is called aluminum. And then SO4, find it on your list of polyatomic ions, and it's called sulfate. And since aluminum and sodium both are special elements on the periodic table that do not need the charge listed, aluminum sulfate is just the name. Let's do 2 more, and let's do ones that have the charge in them, so then you can see some examples of those. Once again, we'll put name on this side, and we'll put formula over here. And let's start one where we're given the name, and we'll go to the formula. So let's do ones that are going to have charges. Let's do iron, 3 phosphate. So the first thing we do is we find iron on the periodic table and realize that that formula is Fe. And since it has a +3 charge given to us by this Roman numeral, we put a little +3 in the upper right-hand corner. And then you'll have to look in your book or on the back of your periodic table, and you'll find that phosphate is a polyatomic ion, PO4, and it has a charge of -3. Now you crisscross people, or you drop and swap people, will then take the 3 and put it here, and the 3 and put it here, and you'd write Fe3PO4. Don't forget to put parentheses around these polyatomic ions, indicating there's 3 of them. And then if you're savvy, you can say, oh, I would reduce that. But if you're a person that just adds them together to 0, then you could say +3 plus -3 is equal to 0. And you'd say, oh yeah, I don't need any subscripts at all. And you wouldn't write the 3 here or the 3 here, because the correct formula is FePO4. No subscripts needed other than the 4 that it comes from being part of the polyatomic or many atom ion called phosphate. Let's do one that goes the opposite direction now. Let's be given a formula, and let's see if we can go to the name. And so this time let's take one that also would have a need of a Roman numeral. Let's do nickel. And let's put it together with some selenium. And, oh, I should do it with a Roman numeral, though. So let's do Ni, and let's not do that one. Let's do NiSO3. That'll seem a little bit more familiar to you. So first name the element, nickel. And you recognize that nickel's one that's going to need a charge, and so you're going to need a Roman numeral, so leave that blank for right now, leave some space. And then you look up SO3, and I just gave you that one in the notes right here if you don't want to look it up on the back of your periodic table. SO3 is called sulfite. Don't change the suffix at all. Remember, it contains a many atom ion, so keep it together. And if you look, sulfite has a -2 charge right here. Nickel, we don't know its charge because it could be many different things because it's in this area of the periodic table. And so we have to say whatever nickel's charge is plus sulfite is going to have to add up and equal 0. Now, if you were a uncrisscrosser person, It wouldn't really work here because there's really a 1 down here, and you'd say, oh, nickel would be positive 1. But you can see from this math that nickel would have to be positive 2. And so you're going to have to put a Roman numeral 2 right here to make it be nickel 2 sulfite. So this gives you an overview of how to do naming and formula writing of ionic compounds, not only the binary ones that have 2 kinds of elements, but also the ones that have multiple elements together that make a many-atom ion-containing compound called a polyatomic ion. Remember, many of these are given in your textbook and also on the back of your periodic table, and you can use those to help find your charges, and then therefore make sure that you use the correct Roman numerals in the middle when writing the names. Good luck.